All right, welcome back to lunch. Here we are on the home stretch, NANOG 61, almost there. I do want to one reminder out to complete the surveys for the content up till now. We have one more drawing for an Xbox One coming up this afternoon, so please fill out the surveys either on the website or via the guidebook. And coming up now, we have Josh Evans with Netflix. Josh.
All right, hello. I'm Josh Evans, and I'm going to talk to you today about fault injection and service resiliency and how we think about that at Netflix. Is this supposed to progress? Here we go. So just by way of introductions, I've been in technology for about 24 years, started out at Borland International in tech support, moved through doing tools development, test framework development, a few management roles, went to a failed startup before I landed at Netflix, and I've stayed there ever since, started there around 1999. So I moved through a number of roles there as well. E-commerce, streaming, and tools, services, and operations have been kind of fundamental to what I've been doing for quite some time. Let me go back one. My current role is Director of Operations Engineering, and I'm going to talk a little bit about what that group is about. But first I want to just introduce you to the Netflix ecosystem and give you a sense of what that's about. So we have many devices out there in the field doing video streaming, for those of you who know about Netflix. We have a control plane in the Amazon cloud, which is predominantly what I'm going to talk about today, but we also do have third-party providers that we work with for static content delivery and authentication services, and we also do have our own CDN. So we've got roughly 48 million customers now and growing. We're in about 41 countries, and we've already announced that we're going to be expanding internationally later in the year. In a given month, we serve up over 1 billion hours of viewing to our customers. And we are on over 1,000 different device types, including DTVs, game consoles, Android devices, etc. We're in 3 AWS regions, and we have hundreds of services that we deploy into each one of those regions. And at peak, we're handling hundreds of thousands of requests per second. And we also, as I mentioned, do have partner-provided services that we integrate with as well. Our CDN serves petabytes of data, stores petabytes of data, and at peak is serving out traffic at terabits per second. And when we think about how we operate all of that and what we want to accomplish, the focus of my team is to try to drive higher quality and higher velocity for Netflix as a whole. And this is a hypothetical graph here showing availability and its tension with rate of change. And the premise here is that as you increase your rate of change, you're going to lower your availability. And if you want to raise your availability, for instance, we would like to be pretty much standing at about 4 nines availability. It seems that you would need to slow down in order to do that. The goal of my team and a larger goal for Netflix engineering as a whole is to try to shift that curve such that we can actually advance on both fronts. And we do that through engineering efforts, we do it through operations, and we do it by evangelizing best practices throughout our organization. And at the end of the day, it's really about a commitment to continuous improvement on both of those angles of attack. So when we talk about availability, it's really this experience that we're talking about. Customers need to be able to sign up. They need to be able to activate a device. They need to be able to browse and find something they want to watch. And when they hit the play button, it needs to work. And this is what keeps us up at night. These error dialogues, I'm hearing some laughs. Some of you might have actually seen this before. And this is something that we are really working to prevent. So the reality is that failures happen all the time. Disks will fail. Your power is going to go out at some point, and generators do sometimes fail as well, so your backup will fail. We're human, and so we're going to introduce bugs into our environment. We're going to make mistakes while we're configuring and operating our environment. And so failure is ultimately unavoidable. So we start out by saying, well, let's design for failure. Let's assume that that's going to happen and do all of the traditional things that you would do to defend against it. So you've got exception handling. We embrace auto-scaling, which I'll talk about in a little bit more detail. We embrace redundancy in the forms of failover, horizontal scaling, and those kinds of disciplines. We embrace fault tolerance and fault isolation so that systems that are dependent on other systems are as resilient as possible when those other systems are unavailable. And we have a concept of fallbacks and degraded experiences so that even if we can't provide the best experience, we can provide an experience to our customers when things are running into problems. So our goal here is to protect the customer from these failures as much as possible. So is that enough? I would argue that no, it's not even close. How do we actually know if what we've designed and what we've coded actually works? Does the system actually work as designed? Is it as resilient as we think it is? And how do we prevent drifting into failure once we've gotten into a good state? Even in the most perfect world, even if we get it all right at one point in time, it will change. And so we test for failure as another strategy. And again, we do a lot of the bread and butter things here. Unit testing at the module level, integration testing at the service level, stress and load tests, and even simulations of testing out various scenarios with combinations of services. And testing does increase our confidence, but that's also really not quite enough, as we've discovered. So testing distributed systems is hard. We've got massive changing data sets. We're at web scale, so hundreds of thousands of transactions per second running through a complex distributed system. The interactions are complicated, the information flows are complicated, and it gets even more interesting as things become asynchronous, and we're moving more and more towards asynchronous models. Third-party services add some interesting variables. We have less control over those. And while we're doing all of these things, we're constantly changing this environment. It's not a static environment by any means. So what if we actually inject failure into our environment? We do it in a controlled way to see how things break. And when we talk about embracing failure, we actually don't talk about a safe version of embracing failure. In our test environment, we actually do it in our production environment. We don't want to wait for random failures to happen, especially at 2 o'clock in the morning. Nobody likes to get woken up at 2 in the morning with a failure and start trying to figure out what's going on. So we want to cause failure so that we can validate our resiliency. We want to test our design assumptions by stressing them with real production load. And we want to remove all the uncertainty, or as much as we can, by forcing these failures on a regular basis, so as we're changing our code base, we can keep affirming that things work as we expect. And so this led to the creation of what we fondly call the Simian Army. And before I get into that, I want to talk about 2 key concepts that are pretty critical to the concept of fault injection. The first one is the concept of auto-scaling, and in the Amazon world, auto-scaling is a virtual instance cluster, or it works within a virtual instance cluster, that scales up and down with traffic. This is a graph of our week-over-week trends, and you can see peaks and valleys as we move into the evening hours and move down into the early morning hours. We rely on both reactive mechanisms provided by Amazon's infrastructure, but we also have our own predictive mechanisms based on these trends. We actually know when things need to scale up, and so we can proactively start spinning up instances as we ramp. A really important factor is not just the scaling dimension, but the replacement dimension. So if we remove an instance from production on purpose to go and try and break something, we want to make sure that it's going to get replaced again with a healthy instance, and so that's a great feature that's provided as well. Another key concept is circuit breakers and fallbacks. And I'm not going to walk through this entire diagram. It's fairly complex, but the concept is that every single request that comes in that's going to go and reach out to a separate distributed system is wrapped in a dependency command object. And if that should fail, if the connection should be too slow, if it should completely fail, there's a fallback built in. And if too many of those happen within a short period of time, we'll actually open the circuit and we will stop sending traffic to that one particular application, to that dependency, so that all the other dependencies and all the other requests can be satisfied and we fail fast until that service comes back up. So let's start with the basics here. Let's start with an instance failing. And this was really, this is related to the first of the Simian Army. This is Chaos Monkey. And Chaos Monkey, you really want to think about it as, imagine that you've let a monkey loose in your data center, and he's pulling out cables and he's pressing buttons, smashing boxes together, and creating kind of random effects within your environment. We obviously do this during business hours because, again, we don't want to get woken up at 2 o'clock in the morning when this is running. But the benefit here is that we get to test this failure on a very regular basis. Our average cluster will have a failure happen every day that's scheduled. That's what we've learned primarily from this particular exercise is that state is problematic. If you have stateless systems and you kill them, they usually spin up very quickly and they can be replaced. If you have state, it takes a while to accumulate state. And for this reason, we've actually taken our time getting around to Chaos Monkey for things like Cassandra, where you actually take out a node and it has to go get replaced and rebootstrapped. Auto replacement works really well, so that's been quite a successful thing for us. But surviving a single instance failure really isn't enough. This is pretty basic stuff. It's been working well for us for quite some time. So let's move up a level, and let's say now your data center fails. In the Amazon world, data centers are called availability zones, and they are clustered into regions. And we created another member of the Simian army, Chaos Gorilla, to take out an availability zone. So we're simulating this. We have a 3-zone configuration in the United States and in Europe. And we eliminate one zone, and then we want to make sure that the other zones can actually handle all the traffic, that things fail correctly. And what we encountered the first time that we ran this, or early on, this was sometime last year, we found that we actually did kind of perturb things quite a bit. This is, again, our starts per second over a much narrower window, and you can see that we induced some variability in our starts per second graph. Few things we learned from this. Large-scale events are really kind of hard to simulate. Taking down hundreds of clusters and thousands of instances in a short period of time is, without actually pulling the power on everything, is actually kind of challenging. Rapidly shifting traffic is also error-prone. We found that our ELBs, the elastic load balancers, we needed to change DNS TTLs so that we could shift traffic more quickly. We had lingering connections between our applications and our caches, and that needed to be addressed. And not all of our clusters were pre-scaled, and so we found that when we started quickly moving traffic around, it took a little while for some of our systems to actually scale up quickly enough, and some of them were not using auto-scaling, and so they needed to be manually scaled. We also learned about some hidden assumptions and configuration issues. Some of our apps were not configured for cross-zone calls. We have a mechanism in our internal load balancer such that if you configure it for zone affinity, which means favor your own zone, and that fails, it will then immediately go and start making calls into another availability zone. And this was not set up for everything, for all of our clusters. There are mismatched timeouts. We have a lower level timeout at our load balancer level, but we also had Hystrix fallbacks that were timing out faster than our underlying load balancer logic. And so we continued to send traffic to the wrong location. Our REST client also had a preservation mode that said, hey, if more than 20% of your cluster just goes away, we're going to assume there's some bug in your code where you're doing something wrong. And so we actually did not release knowledge of instances that had actually been removed. So we sent traffic to instances that weren't there. The good news is Cassandra worked as expected. The hinted handoffs were accumulated on the nodes that were in the existing surviving availability zones, and when we turned everything back on, they replicated back, and it worked quite well. So from a regroup perspective, we realized just recently that we've moved really from zone outage to zone evacuation. We've become a little bit cautious. We carefully deregister instances now when we're doing this exercise. And we're doing more staged traffic shifts. And we're talking now about different ways that we can move back to being more aggressive and simulating a true outage. So let's move up to the next level. Let's imagine an entire region fails. And this would, in the case, would be, let's say, US East 1 or US West 2 in the Amazon region. A whole cluster of data centers goes down at the same time. And what that looks like here, just to give you a little bit of a sense of the architecture at a very high level, is we've got our regional load balancers. We have a technology called Zool, which allows us to deal with misroutes between regions, and it does kind of smart traffic shaping. And it then passes through to the instances within each one of the Amazon availability zones. And of course, Cassandra's running in all those zones and replicating between the zones as well. And we run in the US in what's called an active-active configuration. So we're actually using geo-routing at the DNS level to send roughly half the country to one region and one to the other. Got to stop doing that. So we created another Symbian Army member called Chaos Kong, and Chaos Kong takes out an entire region. And then when it's done, we're able to just go ahead and switch back, and we use this just by changing our DNS routing logic. So what we learned here was this was actually a pretty straightforward exercise, except that we needed to do things like disable our predictive auto-scaling mechanism. We were actually, as we were shutting things down, predictive auto-scaling was scaling our instances back up. So that was kind of counterproductive. We needed to disable that. We also discovered that we really did need to do some pre-scaling in the target region so that we had enough capacity and we weren't really affecting the customer experience in too much of a negative way. So there's still room for improvement, very similar to the Chaos Gorilla exercise. It's not a true regional outage where things go down hard. So we're still doing stage migrations, and we're not doing what we think of as a split brain, where we really cut off the connection between the two regions in terms of Cassandra replication and the Zool misroutes, so that's still work for us to do there. So not everything fails completely. We created a tool called Latency Monkey to test for partial failures, where things get slow, start spewing errors, but don't necessarily go down hard. And so the goal here is to simulate latent service calls and inject arbitrary latency or errors into a particular service level. And then we observe for the effects. Our service architecture, just to expand a little bit, looks something like this as we drill down into one availability zone. We have the ELB, the elastic load balancer, which then routes through our smart layer, Zool, hits the edge, and then the edge will then call many services, sometimes tens or even 100 services, to satisfy a particular request. And Latency Monkey focuses on one of those clusters and treats it as if it's sick. And we do this using server-side URI filters. You can treat all requests the same way, but you can also get down to the request level, the individual request level, using pattern matching. You can also just pick a percentage of traffic that will get the latent or failed response. And we can put in any arbitrary delay and any arbitrary response. So it could be an error code, it could be some arbitrary payload. So what we learned from this, which was interesting, which is, and in some ways obvious in retrospect, that startup resiliency is different from steady state resiliency. Startup resiliency usually involves pulling in dynamic configurations, caching metadata, and doing various things like that. And not all those dependencies were well understood or well known, and so we needed to do some work to try to mitigate some of the concerns around that. Service owners don't always know what their dependencies are. You can be pulling in jar files and other kinds of libraries without really knowing what additional service dependencies are there. And fallbacks can fail too. You can have a fallback that throws an exception or calls another service which is also unavailable. Second order effects are also challenging to test. So this is where service A calls service B, which calls service C. You may call service C directly as well, and it's more challenging with this mechanism to set it up to do that. Dependencies will change over time, so again, even if you get it right now, it might not be correct later. And so a holistic view is really necessary to make sure we're testing this matrix and we're doing that on a regular basis. What we've discovered also is a lot of teams, not a lot of teams, but some teams were opting out because it was just too scary to run this in production for their services to be dependent on a service that we made unhealthy. And so we created yet another set of infrastructure, which we call fault injection testing, which is different from Latency Monkey in some interesting ways. It can be overridden at the individual account level or even at the electronic serial number level for an individual device. And then as you make calls and you have that override in place, the request and the context is decorated such that as it passes through the entire call graph in the distributed system, that override is set so that any service calling a system that needs to be in a sick state will know that it needs to do so. And so we can do things like have edge call service B directly and simulate that failing, but also call service A and have that call service B and get the exact same down effect. So benefits here. This is confidence building so that teams will be more willing to do Latency Monkey simulations at scale. It's continuous, it allows us to do continuous resiliency testing, both in our test and production environment, because this is happening at the request level and it doesn't have any effect on live production traffic. It allows us to test a minimum viable service by turning on fallbacks for all the other services that are not necessary, and keep the main critical viable services up and running and make sure that that actually works correctly. It also allows us to do device resiliency evaluation such that we can learn about how our devices behave when middle-tier services are in a bad state and returning fallbacks. So this is a bit of an eye chart, but this was from our first device resiliency run. All those boxes in red were things that we did not expect to have happen. And in some cases, we had services that should have been optional that were doing things like preventing playback from happening. So we learned a lot from this exercise, and we found it really valuable. So that's fault injection testing. Is that it? And I would argue that fault injection still is not enough. It's really helpful, and it helps us validate things at scale and in many different ways. But we still can deploy bad code and do bad deployments. We still can misconfigure things in production. You can end up with Byzantine failures, complex failures that happen through different interactions and different flows through the distributed system. Memory leaks can happen, and sometimes they take a while to manifest themselves. And performance can degrade and drift over time. And all of these things can lead to availability issues and resiliency issues. So we actually adopt a multifaceted approach that goes beyond fault injection. We're doing continuous build, delivery, and deployment. We're working on that right now. We are shoring up our test environments and infrastructure and code coverage to make sure that we can catch things where possible. We do something called automated canary analysis, where we actually test with live traffic, new code and old code side by side, and then do comparisons to make sure that the new code is at least as good or better than the other code, than the old code. And we do staged configuration deployments so we can isolate a configuration change and learn whether or not it's breaking something before we roll it out broadly. We've got crisis response tooling and operational protocols because things will break, and so the next best thing is to respond quickly. And to that end, we have real-time analytics, detection, and alerting in place. We have operational insight tools that provide dashboards and reports so we can see how things are performing. And we do regular performance and efficiency engagements with our teams to make sure that performance degradations don't turn into reliability issues. So I'll close out by saying it's also about people and culture. Being on a team that is centralized, that is trying to drive availability throughout an organization, it takes some effort to do so, and there's a social dimension to it. From a technical culture perspective, we have adopted the DevOps model of you build it, you run it, and we treat each failure as a learning experience and adopt what's called blameless incident reviews. And this is, we don't want finger pointing within these sessions. The goal here is to get to root cause, figure out what happened, and figure out what mitigation needs to be done. And again, I can't underscore this enough, but a commitment to continuous improvement is absolutely critical here. Context and collaboration are also very important. Context will engage your partners. If you have data and graphs and you can point to root causes and various things to set context with your partners, it helps them get on board. We have many conversations about global responsibility and global versus local, urgent versus important, schedule-driven product type features versus infrastructure investments. And ultimately, we talk about long-term vision about where we want to be, 4 nines of availability, certain levels of latency, a certain value on quality. And so that's something that we're continually working on. In terms of collaboration, if you engage partners as opposed to trying to come up with all the solutions on your own, you're going to come up with better solutions through collaboration, and it also generates buy-in from your partners. At the end of the day, the teams that don't engage, that are on the critical path for your customer experience, are going to be the weak link. So if you're interested in some of the technologies that I've talked about here, a lot of this is posted on the Netflix OSS site at netflix.github.com. And if there are any questions, I can take them now.
Hi, Mike Bennett from 3MG Consulting. I have just one question. During the latency monkey testing, I'm just particularly interested to know sort of the order of magnitude or range of latency that you injected to do your testing.
I believe it goes up into seconds. Most of our timeouts are in milliseconds and small numbers of milliseconds. So it can vary anywhere from add 10 or 20 milliseconds to add several seconds of latency. Ultimately, you want to know what your timeouts are, and then you want to test beyond that limit and see what happens.
Right, great, thank you.
Ram Balakrishnan from Microsoft. And I'm a big fan of your Simian Army. Thank you for taking time to come and talk to us on this. A couple of questions. One is, how much over-provision do you do when you have unleashed this, all this Chaos Monkeys and Simian Army? And what is the guarantee that you have that you don't knock all your redundancies when you have the Simian Army working in tandem?
So I'm sorry, you were asking
The first is
how much over-provisioning we do?
That's right.
So we run in an active infrastructure, so we have enough reserved capacity in either one of our regions to handle 100% of the load. In the regional scenario, we make sure we have enough capacity so that we can handle 100% of our peak load in 2 of our regions.
Okay. And when you have the Simian Army operating in tandem, say for example your Kong monkey and versus some other things, so you have knocked down your whole data center and something else is going on in the other one, so what is the guarantee that you don't knock all your redundancies?
Well, we have to have insight into what's going on at the moment, and we won't actually do the, let's say, the Kong exercise unless we know that everything's in a healthy state. So we're not going to have Chaos Monkey and Chaos Gorilla running, for instance, at the same time that we're doing a Kong exercise. We would separate those exercises out. And if there's some kind of production issue going on, we would hold off and wait until that's resolved before we would go ahead and do that exercise.
So it's a more of a controlled environment. It's a controlled...
Yes, yeah, these are definitely controlled experiments. Chaos Monkey is scheduled on a daily basis for most clusters. Chaos Kong and Chaos Gorilla are scheduled exercises.
Okay. All right. Thank you.
Ethan Katz-Bassett, University of Southern California. Good talk. I was curious if you could talk a little bit about going from injected failures that cause problems to actual root causes and fixes, and whether you've done much in terms of building kind of complementary tools that help in that process.
In terms of trying to discover root causes and fixes?
Yeah, so if you know, one of your monkeys ends up having some effect that you maybe didn't expect, and then kind of the process of going through figuring out what caused that.
It would actually run through our normal protocols in terms of rapid response. We actually don't really pay it for Chaos Monkey. It runs pretty much all the time, and for quite some time has not actually generated any real problems. So we haven't had a situation where it's caused an unexpected incident in quite some time, because teams have gotten used to having it around. That's the advantage of always running it, is people are already thinking about defending against it. The other exercises are done in a very controlled way by the same team that would rapidly respond if something went wrong, and so that helps. So there's scheduled exercises there. I think that might address your question. Did that completely answer that?
Sure, thanks.
Okay.
Scott White, Google. So in that same vein, that preservation mode issue that you ran into, so have those types of things, I'm just thinking about externally, it sounds like some developer thought that was a great idea, and operationally it's not so hot. Have those kind of ideas, have those kind of issues more or less dried up entirely because of this, or have you developed a better process for closing that loop because of this, or other, I guess?
We do tend to learn more the first time we do something, or if we haven't done something in a long time. So a lot of issues got, like with Chaos Monkey, when we first started doing it, we discovered what the problems were, and then they became known. And then teams opted out, essentially, until they were able to get their systems in place so that they could be resilient. So I think that largely addresses that. I suspect when we try to do the next Gorilla exercise and bring things down in a much harder fashion, that we'll learn again that things have drifted, and we'll discover again that there are issues. But the whole point of this is that if you do it on a regular basis, you tend not to get that drift. If you do it very rarely or you don't do it at all, then you're going to get surprised.
Hi, Hugo Slabert, Stargate Connections. More a procedural thing. When you were mentioning you build it, you own it. If that extends down to an individual level, to a team level, and if so, kind of how you deal with continuity. If you have folks entering, exiting teams, or leaving the operation entirely, kind of how you deal with, well, you can't own it anymore because you're not involved.
It tends to be done at the team level, and so there are on-call rotations for a given service, and we try to make sure we've got at least 2 people who know about any one thing. Occasionally you'll have a single point of failure where only one person knows about a particular service, and we see that as a vulnerability, so we try to address that. And then the on-call has an escalation, set of escalation policies such that we'll have a primary person, potentially a secondary person who gets called when there's a service outage. So the ownership is really at the team level, and different teams can do it in different ways. You might have a handful of engineers who do it. Some teams have actually chosen to have more slightly operational people who might address issues, but within the same team. And so it varies a little bit.
Thank you.
Hi, Dylan Green, Microsoft. So a question for you. Have you noticed that this has actually decreased your outages?
I believe so, and that's something that we're actually working on measuring. So our major outages tend to happen extremely infrequently. And so it's hard to tell. Each time I'd say we certainly are not encountering the same problems we've encountered before, but sometimes we encounter new ones. I think you probably heard recently about the Ultra DNS issue. We hadn't tried to do fault injection at the DNS level, and so that had some effects on us that were undesirable. So I'd say it's the thing that we have not tested that tends to be the thing that will break from that perspective. The things that we do test tend to work well.
How about in terms of duration? Do you find that having the experience with the fault injection means that your restoration times are faster because people say, oh, it looks like that?
I couldn't quite hear your question. You're talking about restoration times of
Restoration
service?
times, yeah. So
Yeah.
since you are constantly stressing the system, your engineers happen to know that this kind of failure looks like this, that kind of failure looks like that. Does that mean that your engineers are able to restore problems when they actually occur faster?
It certainly helps. The more experienced folks who have done a lot of these kind of crisis response calls tend to be very good at having a sense of how long it will take to recover. And less experienced people obviously will not. It's hard to know. I mean, there's definitely certain kinds of failures that we've seen before that generally we can respond to very quickly. The other challenge we have is determining when we do something like a complete failover exercise. So for instance, in our active-active configuration, there's an interesting question about, well, it takes about 45 minutes to an hour to move all of our traffic over from one region to another. So it's a judgment call on the moment. How severe is the problem? How long will it take in terms of its duration? Do we pull the trigger and do this very drastic thing to move all our traffic over to another region and then have to fall back or not? And that we just tend to have to deal with that on a case-by-case basis when that happens.
Thank you.
Thank you very much.
Great, thank you.